Okay, so now let's talk about branch prediction. So branch prediction is a really great example of how complicated modern processors are. Basically, they do a lot of prediction. And we will see the need for prediction, branch prediction, in this case, very, very severely, and I'll motivate it. If you want to design a pipeline machine, you have to deal with control dependencies. And I'm going to skip this. Okay, and all of the execution paradigms are actually affected by control dependencies. Doesn't matter what kind of processor you're designing, you really need to deal with the decision-making that goes on, control dependence, somehow. Okay, so control dependence, basically, the key question is, this is a slide that you've seen, I think, before. What should the program counter that you're fetching from be in the next cycle? So clearly the answer is the address of the next instruction you're going to execute, right? But that's a cop-out. Basically, what is that address? All instructions are really control dependent on the previous ones because the next instruction is a sequential instruction, right? So if you're going to the next sequential instruction, the address of the next instruction is the PC plus 4. And we've seen that many times, PC plus the size of the instruction. So basically, if the fetch instruction is a non-control flow instruction, you go to the next sequential instruction. So next fetch PC is the address of the next sequential instruction. If the size of an instruction is constant, this is easy. And we saw that MIPS, the size of an instruction is 4 bytes. In LC3B, it was 2 bytes. That's not the case in all architectures. x86 is a messy architecture where the size of an instruction is not constant. It could be anywhere between 1 byte to 17 bytes. And you figure this out only after you decode the instruction. But that's too late, right? We fetch the instruction. In the next cycle, we want to be able to fetch the next instruction. But we don't know the size of the instruction, so we don't know how much to increment the program counter by. So to be able to fetch the next instruction, we need to decode the current instruction. But it's too late, because once we decode this current instruction, there's a bubble in the pipeline. We didn't know what to fetch. Right? So if you don't know the size of your instruction, you have a problem, actually. Even in a sequential machine, as you can see. But the problem will get worse. So basically, this is easy to determine if you know the size of the fetched instruction. So you can guess, for example, that the next instruction is going to be PC plus 4. That's good. And if the instruction that you fetch is not a control flow instruction, if it's not going to change the PC in a non-sequential manner, that's good. So if the instruction that is fetched is a control flow instruction, then you have a problem. How do you determine the next fetch program counter? There's another question over here. In fact, whenever you fetch an instruction, you don't even know whether the fetched instruction is a control flow instruction, right? Because you haven't decoded it yet. So if you want to treat these control flow and non-control flow instructions differently for some reason, as we will see later on, then you need to also guess that. Okay, and there are a bunch of control flow instructions. These are branch, I'll call them. Conditional branches. When you fetch them, you don't know the direction, whether you're going to go to PC, the next sequential instruction or the target. So there are 2 possible next fetch addresses. And the fetch address is resolved, as we've seen, after you execute the instruction, like BEQ in MIPS, for example, branch equal. It checks the equivalence of 2 registers. And if they're equal, then you jump to the target. There are also unconditional branches. They're always taken. These are the jump instructions in MIPS. So you have only one possible next fetch address. So this is easier to handle clearly because you actually know after decode what is the target address, and it's always taken, meaning you always go to the target address. Calls, they're always taken also, and depending on the call you could have actually a next fetch address that's known after decode. But one makes it easy, of course, right? And they're not, in this case, they're not conditional. When you're doing a call to a function call, actually most ISAs don't have conditional function calls. So it's not a conditional call, it's unconditional. So it's easier to handle. But conditional branches are very hard to handle, so we're going to focus a lot on conditional branches. There are returns. You do a call and then a return. Returns are always taken also, they're not conditional. But they could return to many possible locations because you may actually call a function from many different sites in your program. So you need to figure out what is the next instruction after return. That's really the instruction that comes after the call, right? So there are specific structures in a machine that actually try to predict calls and returns, which we're not going to go into, at least in this lecture. But these are relatively easier to handle. So the hardest ones are actually on the top, conditional branches that we will focus on, and the indirect ones. So indirect ones are basically, they're always taken, but basically in indirect branches, you take a register value and jump to it. You read a register and use that value of the register as the next program counter. So the question is, how do you figure out what's your next fetch PC when you fetched this particular indirect branch? You haven't even executed it yet, right? And it could be anything. It could be any value in the register. In this case, predicting that it's going to be the next instruction doesn't work also, because usually you don't jump to the next instruction, right? An indirect branch is actually very useful if you're done object-oriented programming. It basically helps you to determine the type of object, and you basically jump to a function call that's associated with the object. Okay, if we have time, we may go into indirect branches, but likely not today. Okay, so hopefully it's very clear for you that it's critical to keep the pipeline full. If the pipeline stalls, your IPC goes down, instruction per cycle goes down significantly, or CPI, cycles per instruction, goes up. So there are many potential solutions, and we've seen some potential solutions before. You can stall the pipeline until you know the next fetch address, and based on Frank's lecture, you know that that's not a good idea. Because if you stall the pipeline until you know the next fetch address, you have to stall for every single instruction. Or you can guess the next fetch address, which is the subject of this lecture. You can employ delayed branching. I'm not going to talk about that as much, but you can change the semantics of the instruction in the instruction set architecture. You can say, for example, okay, I have this branch, but I'm going to modify the semantics such that this branch is going to take effect after the next n instructions after it are executed. So basically, this is called a delay slot. The branch doesn't immediately jump to the target if it needs to jump to the target, but always the next n instructions are executed. Let's say the next 3 instructions, which means that if your pipeline is 4 stages, you can put independent instructions in that delay slot, and they're going to be always executed. So this is a potentially cool idea, but the problem is, how do you find those n instructions over there? So if we have time, we'll get to that. But this is another solution by changing the semantics of the branch instruction. Right now, we say that branch takes effect right away. If it needs to jump to the target, the next instruction is definitely not executed. Right? We know that. Next sequential instruction is not executed. You can change the semantics such that even if the branch jumps to the target, next instruction is executed. And you can change that value n. You can say n is 5. The next 5 instructions are always executed this way. You can keep the pipeline full. Now it's the compiler's job to put instructions into those delay slots that will always be executed, even if the branch goes to the target address. Now it turns out, actually MIPS, the architecture that you're looking at, has a delay slot, branch delay slot. We didn't cover it. Because delay slot is a mess, actually. It's not very nice. It's one of the mistakes in the instruction set architecture. You should not solve the branch problem this way. Because what it's really doing is you're tying the pipeline length to the ISA, which is not good, because your pipeline length might be 2 stages today, which means that you may need 1 delay slot. Or if your pipeline length becomes 20, what do? Do you have 20 delay slots? Not good. So that's why we didn't cover it. But remember that this is one way of solving the problem. Do something else. You've seen fine-grained multi-threading. Basically, this eliminates the problem. The idea is you have multiple threads to fetch from, decode from, and every cycle you fetch from a different thread. And threads are independent of each other. If this is the case, you don't need to do anything when you fetch an instruction from one thread, because you don't need to predict the next instruction that you're going to fetch, because you're going to fetch from some other thread. And if you have more threads than the pipeline stages, this works great. You never need to predict branches. You never need to handle data dependencies, as we've discussed, right? This is a very cool idea. And GPUs actually employ this. We're going to talk about this when we talk about GPUs. GPUs actually are fine-grained multi-threaded machines. They don't do any dependency checking or any branch prediction within a single thread, because they have enough threads to fetch from so that they can keep the pipeline full. But of course, if you want to improve the single thread performance, again, I gave you the example of I press this button and I want to improve the latency of that, right? And I cannot parallelize that. This doesn't help me. You need to really improve that sequential code performance. Okay, or you can eliminate control flow instructions. You can convert the control flow dependence to a data flow dependence, which we may get to later on. Yeah, think about it in your head right now. If you can do it, you get rid of branches. The problem is you cannot do it for all branches. Like if you have a loop, you cannot eliminate the branch over there, because by definition, loop needs to branch so that you actually keep executing the loop. Right? And this has other problems also that we're not going to go into. Or this is actually an interesting idea also. Whenever you get to a fork, take both paths. Right? This is called multipath execution. Whenever you get to a branch, you don't know which one to execute, so follow both paths. This is additional hardware, of course. It's costly. And if you get to another fork in either of the paths, what do you do? So this becomes exponentially complex, actually, as you keep doing it. Yes? You can think of it that way too, maybe, yes. But it becomes very, very costly to do it. Okay, so we're not necessarily going to cover all of them, although we clearly covered the first one, stall the pipeline, but I'm going to go over it again. So if we actually want to stall the fetch until next program counter is known, the question is it a good idea? So assume that we have a non-control flow instruction here. We just fetched it. We're being strict. We're not going to predict that it's the next instruction is the next sequential instruction. We're going to say, I'm going to stall the pipeline. Now, if you do that, you're not going to fetch any instruction in the next cycle because you don't know what the next program counter is, right? So you need to wait until this instruction is decoded. And after you decode the instruction, you figure out it's a non-control flow instruction. Then you can fetch the next instruction, right? Now, this is not a great thing. Basically, we designed this pipeline, and we're fetching an instruction every other cycle. And this is the case with non-control flow instruction, or a jump. Assuming the jump, you can resolve it in the decode stage, right? So this is not great. Basically, we've immediately ensured that our maximum throughput is 0.5 instructions per cycle, even though we can fetch one instruction per cycle. So that's why you need to predict branches, or you need to handle them somehow. Okay, so let's talk about the importance of the problem a little bit. So people have found out that these control flow instructions are very frequent. For example, if you're doing a decision on a query, you actually have a lot of control flow. So it could be between 15 to 25% of all instructions. So the problem is, next fetch address after a control flow instruction is not determined after n cycles in a pipeline processor. That n cycles is called the branch resolution latency, minimum. It could be maximum also. If it's dependent on a load, for example, it could take a long time to resolve that branch. So if you're fetching W instructions per cycle, that's superscalar width. That's the width of the superscalar execution. The pipeline is W wide. A branch misprediction actually, if you mispredicted a branch, you waste a lot of things. So assume that you're predicting the branch, and the branch resolves after n cycles. By the time you know the address of the target, and by the time you know whether you should branch to that target or not, you've already fetched n times W instructions into the pipeline. Right? For example, if you have a 5-stage pipeline, the branch resolution latency is 4. At the 4th stage, you figure out, at the ALU stage, you figure out whether the branch is taken or not taken. And if your pipeline width is 3, in that case, n is 4 and W is 3. Basically, if you fill the pipeline with 12 wrong instructions, if you do that. If you stall, you have a similar problem, basically. So misprediction is also not good. Does that make sense? Okay. So now let's do this exercise. Assume we have n equals 20, a branch resolves after 20 pipeline stages, which is not unreasonable. Pentium 4, a branch resolved after 20 pipeline stages. Pentium 4++, Prescott, the pipeline length was 29 stages, actually. And your width is 5 wide. I picked 5 here because it's going to make the calculations easier. What is our IPC going to be? So we're going to assume 1 out of 5 instructions is a branch. And we're going to assume each 5 instruction block ends with a branch. So we're going to fetch 5 instructions, and the last one is a branch. Assume this always. So the key question is, how long does it take to fetch 500 instructions? But of course, I didn't give you enough information. the first part of the question is, what if you predicted all of the branches correctly? If you predict all of the branches correctly, meaning you know what's the next 5 instruction block you're going to fetch, you're fetching 500 instructions in total, and every cycle you're fetching 5 of them, which means that your IPC is 100, basically you finish everything in 100 cycles, right? Yes. IPC is 5, yes, exactly. Yeah, there you go. Basically, it takes 100 cycles to fetch all instructions because you're fetching 500 instructions, and every cycle you're fetching 5 of them. So 500 divided by 5 is 100 cycles. And IPC is instructions per cycle, 500 instructions per 100 cycles. So this is great because this is your maximum IPC, right? And also no wasted work because you always fetch right instructions. So of course, I should also say that we're not assuming any data dependencies here. Everything, there's no data dependency in this machine or in these 500 instructions that you're fetching. Okay, let's make the accuracy 99%. So basically, out of these branches, out of 100 branches, and remember that we actually have 100 branches here, 500 instructions, 1 out of 5 instructions a branch, so we have really 100 branches that we're fetching. One of them is wrong, meaning one of them you predicted incorrectly, and you fetch some wrong instructions into the pipeline, and you need to flush them, get rid of them. What is the impact of this? How long does it take to fetch 500 instructions? Anybody? Any takers? There's an easy way to calculate this. Yes?
Since there are more than 5 instructions per branch, there'll be one branch.
Yes.
And that was basically a whole pipeline.
Exactly.
So that is the extra.
Exactly. So basically, you've done it the way I would think about it. Basically, you need to finish 500 instructions for sure. So you need to take 100 cycles to finish all of them. But once out of those, you do it wrong, basically for 20 cycles, you're on the wrong path, right? Because you have 100 branches over here, one of them is wrong, and for one of them, you pay the penalty of being on the wrong path for 20 cycles, and then you figure it out, you flush the pipeline, and you fetch from the correct instructions. So it takes 120 cycles. IPC is therefore 500 divided by 120, which is not terrible. It's still, it's close to 4 now, right? It's not 5. But you also fetch 20% extra instructions. So assuming that this correlates with the energy you consume, you increase your energy consumption by 20%. Okay, let's go down to 90% accuracy. Any takers? How long does it take to fetch 500 instructions if you have 90% accuracy? That's good, yeah. Basically, you can think of it again. You definitely need to fetch for 100 cycles to finish all the instructions, but now you're paying extra penalty. 10 out of the 100 branches are wrong, because it's 90% accuracy, and for each of those 10, you're basically wasting 20 pipeline stages. So you basically take 300 cycles to fetch all of them. So now your IPC tanks, it becomes 1.6, and you're now fetching 200% extra instructions. So both your performance goes down, your energy increases. You're doing useless work on top of the fact that you're not utilizing your machine well. Okay, let's go down to 60%. 60% is still good, right? It's better than random guess. Random guess is 50%. So that's 900 cycles, which means that your IPC is now below 1, 5 divided by 9, but your machine is capable of finishing 5 instructions per cycle. Clearly, you're not finishing 5 instructions per cycle. You're not even finishing 1 instruction per cycle. And your extra instructions is 800%. So that's the importance of the branch problem. If you have a wide and deep machine, if you're not able to feed, so this is better than random chance. If you're not able to feed instructions with a very high accuracy, you're basically not getting good performance and you're wasting a lot of energy. So we're going to see in the remaining part of the lecture how we actually get close to 99%. So we're going to be much better than random chance. Okay, so we can take a break right now. Let's continue. So now I have hopefully convinced you that branches are a very important problem. And that's exactly the reason decades of research was dedicated to solving this branch problem. Now it's one of the hardest problems in computer architecture. How do you predict the branch, basically? How do you predict what's coming next? And we're going to see a bunch of different techniques toward this end. So we're going to basically talk about branch prediction. So basically, the key idea is very simple. You guess the next instruction to fetch. You don't stall. You basically guess. So stalling fetch, this is, again, you can animate this on your own. For example, if you have this branch, you can go this way or this way. If you stall fetch, you definitely wait until the branch is resolved. Assuming the branch is resolved over here, you basically wasted a bunch of pipeline slots, as you can see, right? You basically waste all of these white slots. And then you can fetch from the target. But if you do branch prediction, you basically guess the next instruction is either the next sequential one or the target, and then you fetch it. So you keep the pipeline full. And if you're correct, that's great. You can basically reduce, in this case, 12 cycles to 8 cycles. But you know that the impact is much larger if the pipeline is deeper. If the branch resolves after 20 cycles, like what we've seen, you have a much bigger impact. And if you are fetching multiple instructions per cycle, W instructions per cycle, like 5 instructions per cycle, as you've seen, you have a much bigger impact, right? So a misprediction, of course, the downside is if you fetched the wrong instructions, meaning if you guessed wrong, what's the next instruction to fetch? You need to get rid of, unfortunately this became green somehow, but you need to get rid of these instructions that you fetched wrong. And then you need to start fetching from the correct path after that. So you have a misprediction penalty in this case. So all of these parts, unfortunately, they shouldn't be green, they should also be white. They should, basically these are useless. And all of these other slots in the pipeline, you didn't fill because you need to restart the pipeline with the correct instruction. Okay, so now that we've seen that's branch prediction, how do we predict what is the next address? So the simplest one is always guessing the next PC is PC plus 4, next sequential instruction, right? So this is a form of next fetch address prediction, and also branch prediction, because you're predicting that the next instruction is the next sequential instruction. Of course, it turns out this is not always. This is good if the next. So if you're looking at just a branch, this is accurate by for 30. The accuracy of this is about 30% or so in real programs. Not good, right? So people have developed ways to make this more effective. So the idea is relatively simple. You need to maximize the chances that the next sequential instruction is the next instruction to be executed. Now, what does this mean? The compiler can actually change the structure of the code, the control flow graph, such that the next sequential instruction, or the likely next instruction is on the not taken path of a branch. So let's take a look at that very quickly over here. It's a simple idea, and it's used in pretty much all compilers of the world. Of course, you need to have a guess of what's the likely taken path. So let's assume that this is our control flow graph, block A, and then you have a conditional branch, let's say BEQ. Oh, you cannot see, that's a, yeah. Okay. I thought it was all automatic. We don't have artificial intelligence yet. Where is it? Okay, well, I'm going to make this fit, but it's not going to work. Anyway, I think we'll make do with this. Because I hope I won't need more space than that. But how do you actually change this? Do you know? Turn the camera. How do I do that? What is the other way? Oh, okay, I see now. Thank you. Wow, that solves the problem, huh? But now the focus is broken. Hopefully you'll be able to see. Basically, autofocus off. Is it better? There's still some issue, but anyway, hopefully you'll see the basics. So basically this is B, block B, this is block C, and then block D. Basically, this is a control flow graph, meaning this basically gives you where the control should flow. So for example, this could be an if, and then I guess if, ... you do B, else you do C, and there are a bunch of instructions here, and then you have D over here, and then you have A, which ends with the if. Make sense? So your code looks like this in the control flow graph. Now, if you actually have this sort of control flow graph, and if you look at the memory layout of the code, one thing the compiler could do is start A here, put B here, put C here, and put D here, right? Make sense? So now the conditional branch is here. And if you're predicting next program counter is PC plus 4, it better always be, almost always be the case that B comes after A, right? Because in this case, this is the program counter, this is program counter plus 4 for the branch, right? Whereas if the compiler has another choice, it could lay out the code such that you have A here, this A starts from here, C starts from here, B starts from here, and then D is here or somewhere else. Let's ignore D for now. So if most of the time the path you take is from A to B, basically branches, you almost always execute this if block, this is a better layout, right? Because you're predicting next program counter is PC plus 4, and when you get to this branch, it's likely that it's going to be taken this way. So your prediction is correct. So let's assume that this is 99% of the time you're going from A to B in code, 1% of the time you're executing going from A to C. You'd better lay out your code this way, such that you basically go sequentially, such that your prediction is always correct for that branch, or almost always correct for that branch. Right? Makes sense. So that's the idea, basically. You lay out the code such that the most frequent transitions are consecutive in memory, so that your prediction next program counter is equal to PC plus 4 is almost always correct. Make sense? So now there are multiple questions over here which the compilers need to tackle in real life. One question is, how do you figure this out? How do you know that it's 99%? So what the compilers do today is they do profiling. They basically profile some input sets, run the program with multiple different input sets, and they figure out, okay, out of all of the runs of this branch, the branch was 99% going this way, A to B. So they can figure this out by running the program multiple times, right? This is called profiling, basically, input profiling or program profiling. Of course, it's heavy, because before you run the program, you need to actually do these many runs. Of course, this is an issue, right? You may, after you run the program, you may figure out that this is 99%, but when the actual input set, the branch may actually go the other way most of the time, right? This is your profiling, and the profiling can say, okay, according to all of the runs that I've seen, 99% of the time A goes to B this way. But when you really run the program, it turns out 99% of the time, this transition gets exercised, and this becomes 1%. So the compiler laid out the code this way, assuming that hopefully the branch will go this way 99% of the time. But in real life, the branch goes 99% of this way. So you really needed this one, actually, but the compiler gave you this one. So the prediction accuracy now becomes 1%, assuming you have a prediction that says next PC equals PC plus 4. So this shows you the importance of a compiler, right? But this is tough, this is not easy, profiling. So basically, profiling is always subject to the representativeness of the input set. If I can write. Basically, if this is the case, if you thought that this was 99% and this was 1%, and you got exactly the opposite, your input set was likely not representative. You tested the program with some input sets that were not representative of the real run of the program. And this is a very tough problem to solve. People have tried to figure out representative input sets, but it's not easy, because your data can be anything depending on your program. Okay, but now this shows you the power. The compiler can make the prediction accuracy 99% or 1%. Right? 1% prediction accuracy is terrible, clearly, because 60% was terrible, as you've seen before. Okay, so that's the idea. So software can actually have an impact on how full the pipeline is. Of course, you need to know the branch prediction. mechanism. In this case, the branch prediction method is simple, but the software needs to be complex to keep the pipeline full. So there's this is actually introduced in programming language design and implementation in the seminal paper in 1990, and it's employed in all modern compilers. And if you really are interested, you can read this paper. There's also a hardware way of doing this I'm not going to go into. Basically, hardware internally reorganizes the code such that you get good prediction accuracy. It's internal, it's not visible to the software. In this case, clearly, the first one was visible to the software. This is called the idea of trace cache, and you've seen it actually in the Pentium 4 diagram that I showed you, but I didn't talk about it, and I'm not going to talk about it. But you can actually do this, something similar in hardware, purely in hardware as well. So it's always good to have the mindset, whatever you can do in software, you can actually also do in hardware. If you have unlimited resources, these are, in the end, what you have is a Turing-complete machine that you can use it for any purpose. So if you can do it in software, you can do it in hardware. And if you can do it in hardware, you can do it in software also. But you need to have some basic support for software, of course. Okay, yes? Mm-hmm. Yeah, so in this case, you mean for this one, right? Yeah, basically, people try to keep everything inside the caches. Yeah. It still helps, yeah. Yeah.
If it is on a software level, so it is visible, it is part of the ISA, right?
No, this transformation is not part of the ISA, because ISA just specifies a memory layout for you. It's basically where you order. But you do change the program counter of different things, yes. Mm-hmm. It is visible, yes, absolutely. It's at the software level. So the programmer, when they debug the code, they may need to know where the memory is laid out. Yes. Okay, so this is one way of making it effective. How else can you make this more effective? If you're guessing the NextPC's program counter +4, you get rid of control flow instructions. Again, or minimize their occurrence somehow. So there are two ways of doing it. One is basically use less branches in the code. This is called predicate combining. Basically, if you have a lot of branches in your code, maybe you can combine them into a single branch. For example, if you're checking if A is greater than 500, and then branching on that, and then checking B is greater than 10,000, and then branching on that, and then checking C is greater than something, you can combine all of them. You can have a single if statement saying if A is greater than some number, and B is greater than this number, some number, and then and C is greater than this number. You can have a single branch that combines all of them. That way you got rid of 3 branches. It became only 1 branch. But of course, this has some downsides as well, because you actually execute more code sometimes. I'm not going to go through this in detail, but you can think of this as a programmer also, right? If you have a lot of ifs that are separate, you may think about combining them. And the compilers can do that for you as well. Or you can convert control dependencies into data dependencies, which we're not going to get into right now. But that's another method of getting rid of branch instructions. So let me give you the example very quickly. How do you convert a control flow dependency into a data flow dependency? You need ISA support for this. But you could implement this with branches, or you could say, let's assume that this is A. So A, yeah, something like this. I didn't want to get into this, I guess, yes. So basically, this is kind of like a data flow dependence, right? If you think about a branch, you can express a branch as a data flow value also, in this, at least in this case. Basically, let me actually do this. So you have a D over here. D may get the input from C, assuming they're dependent. So you basically, oh, you cannot see it. Okay, so you basically need to select. Remember the select node from the data flow? It's essentially a branch. In the data flow graph, you had a select node that selects whether B gets connected to C, or whether D or C gets connected to D, if there are dependencies over there. Again, I'm not going to go through this, but you can take a look at the data flow graph that we had. We may get back to this later on. But let's assume we're doing branch prediction, which is the common method. Predicate execution is employed in some processors, but not a lot today. ARM used to have a lot of predicate execution. For example, they got rid of it for good reason. but maybe they don't need to get rid of everything. Okay, so basically if you assume that instruction H is a branch over here, the condition and target are evaluated in the ALU stage. It takes 3 cycles to finish the branch, right? And when a branch resolves, you basically fetch the instructions from the right target, and the instructions that are fetched since instruction H needs to be flushed. I've shown you this already, but this is another picture of it. So the wrong path instruction must be flushed. In this case, you basically fetch 2 wrong path instructions because the branch resolves in the ALU stage, and you fetch the next instruction, the fetch in that next cycle. So you basically need to flush the 2 instructions that come after the branch. So kind of kill them. Okay, so let's do some calculations, some more performance analysis. Basically, you can, for a correct guess, you have no penalty. For an incorrect guess, you have 2 bubbles in this case. I'm going to go through this very quickly because I've already motivated this, but I'm going to use this to make another point. So assume that there are no dependency-related stalls, and you have 20% control flow instructions, and 70% control flow instructions are taken. This means that your CPI, cycles per instruction, is 1 in the regular case to finish all instructions, but you have some penalty. The penalty comes from the mispredicted branches. So 20% of the control flow instructions are control flow instructions. So 20% of the time, you have control flow instructions, and 70% are taken. So 70% of the time you're wrong, because we're assuming PC, next program counter is PC plus 4 when we do the prediction. So for 20% of the time, you do a prediction, and 70% of the time you're wrong, and when you're wrong, you pay a 2-cycle penalty. So essentially, 86% of the time you are correct, but 14% of the time you pay a 2-cycle penalty, and that increases your cycle per instruction to 1.28. So this is really the probability of a wrong guess across all instructions, and this is a penalty for a wrong guess. So ideally, you would like to minimize both, right? The penalty for a wrong guess was 20 in the previous example. That's why we actually reduced the performance a lot. So the probability of a wrong guess, 86%, is not terrible, actually. So the key question is, we would like to reduce either of the 2 penalty terms. Let's take a look at this one. You've seen this before. But how can you reduce the penalty for a wrong guess? If you go back to this pipeline structure, you can essentially add, as opposed to finishing, resolving the branch in the ALU stage, you add extra logic to resolve the branch earlier. Basically, if you're checking if 2 registers are equal, you just add extra logic to check 2 registers are equal after the register file over here, as opposed to doing it in the ALU. Now you've reduced the penalty term to 1. That's the penalty for a wrong guess. You didn't change the probability of a wrong guess because your branch prediction algorithm is still next program counter is PC plus 4. But you reduced your cycles per instruction, which is good for performance, right? It's, as opposed to 1.28, you have 1.14. But you've added extra hardware. Now the question is this a good idea? Any guesses? So performance is not just about cycles per instruction. It's also about clock cycle time. Never forget that. You may actually reduce your cycles per instruction, but now you've added potentially something that gets in your critical path. You read the registers, but not only read the registers in this stage anymore, but also check whether the registers are equal. So if this lengthens your critical path by more than 14%, you have a problem. Right. So it's really a trade-off between cycles per instruction and the clock cycle time. Okay, I think you've seen this earlier, so I'm not going to dwell on this. No, never forget that clock cycle time is also very, very important. Okay, so let's do a little bit more enhanced branch prediction right now. I've given you one particular way of doing branch prediction, and we're trying to predict the next fetch address. This actually requires 3 things to be predicted in the fetch state, not just one thing. Whether the fetch instruction is a branch, if it's a branch, what is the direction of the branch? And this matters for conditional branches. And if the branch is taken, what is the target address? So if the branch is taken, you need to know all of this, basically. So let's take a look at the branch target address, because branch target address, even if you have an unconditional jump, if the target address is resolved in the decode stage, you basically waste 1 cycle, right? So people have figured out ways of remembering the branch target address. The first time you execute the branch, you record it somewhere, that's the target address. Next time you see the branch, you get it from that somewhere. Now you guess the target address while you're fetching the branch, And if you can quickly tell that it's a branch, you can feed back that guessed target address into your program counter. So you need this also, basically, whether the fetch instruction is a branch. So the observation, why this works, is target address remains the same for a conditional direct branch across dynamic instances. This is also true for unconditional PC plus offset-based branches, clearly. So if your target address is always the same for the same static branch, if you execute it once, the target address is the same. Next time, the target address is the same. For the example over here, if then else, the target address is the same, right? One of the targets is PC plus 4. That's easy to calculate. The other target is whatever the beginning of this this memory address is, essentially, for that block. So the idea I already told you, store the target address from previous execution of the branch. You execute it once, you calculate the target address, store it somewhere in some small memory structure. And the next time you access the program counter at that location, you can immediately get the target address. Essentially, it's some special memory to remember what the target address was for that particular program counter. This is called the branch target buffer or branch target address cache. So let me give you a pictorial way of thinking about this. So you have a fetch stage, you have a branch target buffer. You can think of branch target buffer as a cache of target addresses, recently seen target addresses. And you also need to predict the direction of the branch. So you have the program counter of the instruction. That's the address of the current branch. You access the branch target buffer, and you access this also concurrently. If you hit in the branch target buffer, meaning the branch target buffer says, oh, I have a target for you for this program counter because the last time I executed, the machine executed the instruction at this program counter, it calculated a target address, and we wrote the target address into this particular memory structure. You get it, you get the target address from here. And you also get a signal saying, okay, I have a target address for you in this program counter. We're not going to talk about how we design the structure yet. We'll talk about it when we get to the caches. But assume a structure, if you recorded a target address associated with a PC, the next time you ask for the target address for that PC, you get the target address and it gives you a hit. If you never recorded a target address associated with a program counter, you don't get it. And this structure tells you it's a miss, it's not a hit. Make sense? This is like an associative memory, actually. It's very similar to the content addressable memory that we've seen earlier. Okay, so this is how you get the target address. Whenever you execute the branch first, you write the target address here associated with the PC. And the next time you execute the branch, you ask the question, is there a target address for me that's recorded? If the answer is yes, you get a hit, a 1 in this signal, and you get the target address. Concurrently, in the same time, you need to ask the question, is this branch going to be taken? This is for a conditional branch. We're going to focus on conditional branches. This program counter accesses some structure. Let's call the branch direction predictor. And this tells you whether the branch is predicted to be taken or not. And if the structure says it's taken, you have logic that basically decides what's the next fetch address. If the branch is predicted to be not taken, this is 0. You select PC plus 4, let's say, assuming you know the instruction size. Next fetch address is PC plus instruction size, and you don't care what the target address is. If the branch is taken, and if this is a hit, then you use the target address that you previously calculated, that you got out of the ETB in this cycle as your next fetch address, and you put it into the program counter. Make sense? Now, if the branch is predicted to be taken, but you don't hit in the BTB for some reason, you basically use PC plus 4 as the prediction. So if you don't have the target address, you use the next sequential instruction as the prediction for the next fetch address. So this is what a very basic front-end branch prediction logic actually looks like in an existing machine. Now the question is, how do you actually design this direction predictor? So if the direction predictor is next fetch address is PC plus 4, you clearly don't need this, right? Because you never predict that the next fetch address is going to be the target that you calculate. So this doesn't work. This is not needed if you're always predicting PC plus 4. This is needed if you're sometimes predicting PC plus 4, sometimes predicting the target address. So a more sophisticated branch direction prediction, actually, we'll see that. We're going to use actually other stuff to guess what the direction is. For example, we're going to look at what other branches, what direction other branches went to. This is called global branch history. And it's going to make sense when we discuss it, because there's correlation between where the different branches go because of the code structures. Okay, so I've already given you this. Basically, the third one, branch target address prediction, can be accomplished using a BTB. You remember the target address computed last time the branch was executed. The first one also can be accomplished using a BTB. Basically, if the BTB, branch target buffer, provides a target address for the program counter, then it must be a branch, because you recorded it, right? You don't record a target address into the branch target buffer if it's not a branch. You record only when you finish a branch. So branch target buffer is actually very useful because it gives you the branch target address, and if you get a branch target address, you implicitly know that this must be a branch. Because in the previous execution, this program counter was associated with a target address. Or you can do other things, but I'm not going to talk about it. The paper that you read actually talks about that a little bit. So you can do other stuff. But BTB is a very good way of doing this. So now let's concern ourselves with how do you actually predict the direction of the branch? This is the hardest part, actually. So we're going to talk about some direction prediction schemes. Some of them are static, compile time. I say compile time, even though the hardware does it, compiler actually plays a role by reordering the code to make these very effective. And some of them will be runtime. And we will see the runtime ones are actually much better than these static ones. Okay, so let's start with the static ones. We've seen always taken, actually. We've seen always not taken. So always not taken is next, the address of the next instruction fetch is equal to PC plus 4. So it's simple to implement. No need for BTB, no need for direction prediction. Hopefully that's clear. Now, unfortunately, it's low accuracy, as I said. It's for conditional branches, you get 30 to 40% accuracy. It turns out people have done a lot of studies and they figured out most of the branches are taken. Why? Because a lot of the branches are actually loop branches. If you're looping, if you have some loop that you're executing a lot of the times, that's usually taken. Okay, but clearly you can potentially make this more effective, although it's not easy to do if you have a special loops. Compiler can lay out the code such that the likely path is not taken path. So we've seen this. The next step is predicting always taken. If this is low accuracy, flip, basically predict always taken. Again, you don't need direction prediction because you're always saying, whenever you see a branch, you say, oh, I assume this is going to be taken. You just need a BTB in this case. And this leads to better accuracy, 60 to 70% already, because most branches are taken. Most in this case means that more than 50%. Interestingly, most has two meanings. Most sometimes may mean that overwhelmingly most, like 90%, but that's not the case here. So the reason is, again, loop branches are usually taken, and this is also sometimes called backward branches. Backward branch means that the target address is lower than the branch program counter. Okay, so people actually figured out that these backward branches are usually taken, meaning if the target address is before the program counter, if your code layout is in some way, because you loop back and then you execute the same code again and again and again in a loop. These are usually taken. But if you have a forward branch, it's not as much taken. This is, again, based on profiling, lots of profiling of code. So this is another mechanism. If it's a backward branch, you predict that it's taken. If it's a forward branch, you predict that it's not taken. So predict the loop branch that's taken, all other branches that's not taken. So this leads to better accuracy, slightly better accuracy. Of course, the logic is a little bit more complex right now, right? You need to figure out what's a backward branch and what's a forward branch. But you can store that information. The first time you execute the branch, you can store that information in the branch target buffer. The branch target buffer can have another bit saying, oh, this branch is backward or forward, because you've decoded the branch, you know the target address, you know the program counter. You can compare both, and you can say this is backward or forward. Okay, so these are static mechanisms. There are other static mechanisms. We're going to talk about this one. This is actually very interesting because now the compiler plays a bigger role. Profile-based. Remember, we talked about profiling. Compiler profiles the code, figures out which direction branches go. The compiler can do it, and the compiler determines the likely direction for each branch, and encodes that direction as a bit in the branch instruction format. So let's assume that we change the branch instruction format. We have a single bit that is set by the compiler or the programmer. In this case, it's compiler. The compiler profiles the code and says, this branch whenever I execute it in my profiling runs, it's 99% taken. So I'm going to set that bit as 1, indicating to the machine that this branch is likely going to be taken. Now the compiler is giving a hint to the machine, based on all of the information that it has about the program, this branch is going to be likely taken. Now, this is good because the machine has more information. It didn't do anything, but it got this information from the compiler. So what is the benefit of this? So this is interesting because all of the prior mechanism, always taken, always not taken, backward taken, forward not taken, you don't distinguish between different branches, right? But there are different branches, there are different if and else statements in the code. Not all if and else statements are equal, not all branches are equal. A loop branch is clearly not very equal, and some loops may execute 1,000,000 times, some loops may execute only 1 time, right? If the compiler has this information, it can basically encode a different 1 or 0 for each different branch. So as a result, this immediately leads to higher accuracy, because now you can distinguish between branches. Of course, accuracy is always a question of how representative your profile is, as I showed you in the previous example. If your profile is not representative, you may actually get worse performance compared to the other schemes. But here you can get per branch prediction. Of course, the other downside, other than profile being not representative, which is the next part, this requires hint bits in the branch instruction format. So your branch instruction format is not just opcodes and the bits that you need to calculate the target address. You just need another bit saying, what is the compiler predicted direction of this branch? Make sense? And you can, so how do you actually make use of this hint bit? The first time you execute the branch, maybe you don't use it, maybe you use it some way, but you store this hint bit in the BTB, and the next time you fetch this branch, you quickly access the BTB and you basically take that bit and use that as part of your prediction. Okay, so the accuracy depends on dynamic branch behavior. So if your branch is always taken, so I made up a dynamic branch execution here. The first 10 times the branch is taken, the next 10 times the branch is not taken. Assume that, I don't show it over here, but if it's always taken, if it's all T's, you get 100% accuracy. If it's all N's, you get 100% accuracy because the bits, assuming the bit is correct. But if your branch changes behavior like this, the compiler cannot encode this behavior with a single bit. Right? Basically, the compiler says, okay, assuming even the profile is the same as the real execution, the compiler picks one of them, but you get 50% accuracy, regardless of what the bit is set to. In this case also, taken, not taken, taken, not taken, taken, not taken. If that's the execution of the branch, you get about 50%, exactly 50% accuracy. And accuracy depends on the representative of the profile input set I've already discussed. So there are some cases where you cannot predict, but if you look at these patterns, they're very predictable, right? If the hardware sees this pattern, if you have a pattern matching logic in the hardware, you can easily predict based on that pattern that, in this case, you always say, I'm going to do exactly the opposite of what the previous outcome was. If it was taken, I'm going to predict it not taken in the next time. If it was not taken, I'm going to predict it taken next time I see the branch. Because you're executing the branch many times. You see this PC once, the PC comes again at some point, the PC comes again at some point, again at some point. So you always make a decision based on the previous time. Make sense? Okay, so keep that in mind. So that's another interesting part. Basically, you can have static branch prediction that's program-based or program analysis-based. And this is a seminal paper by Tom Ball and Jim Laris. Jim Laris is the dean of School of Engineering, actually, or computer science at EPFL. He was at Microsoft Research before. So basically, this is a very interesting work that basically says you can use heuristics based on program analysis to determine statically predicted direction. Now, what does this mean? You don't even profile the program. You don't run the program as a compiler. The compiler basically analyzes the code. So what is the analysis it makes? For example, this is one thing that these folks have found. If the branch is branch less than or equal to 0, it turns out most of the time the branch is not taken. Basically, you can build this knowledge somehow. You don't need to profile the particular program, but maybe across many, many programs that you've seen in the past, you say, if the branch is branching less than or equal to 0, predict it as not taken. It turns out negative integers are used as error values in many programs, and if you're checking for a negative integer, predicting that you're not going to take the branch is a good idea. Or loop heuristics. Usually programs execute the loop, so if you have a branch that says if x, execute the loop, that branch is usually taken. So you can predict that as taken. And the compiler sets a bit again in this case. So if you're comparing 2 pointers in a program, you might guess that they're not equal most of the time. Again, this is a heuristic based on understanding of the code, based on understanding of the many of the programs. Or if you're comparing 2 values, floating point values, you can predict that they're not equal. So the upside of this is it doesn't require profiling. It requires a set of figuring out what the heuristics should be, but it's not profiling. You don't need to run the code. But the downside, again, is your heuristics may not be good. If your heuristic is wrong for some reason, for this particular program, you don't get the benefit. And similarly to the previous one, this requires compiler analysis and instruction set architecture support. That's true for other static methods that we've seen. Okay, so it turns out actually this gives you 20% misprediction rate as reported in this paper about 26 years ago. I don't know how it is right now. Okay, there's another approach. This is programmer based. This is very similar to what the compiler does. Compiler says this is the likely, if I have a branch, I'm predicting that it's going to be likely taken or likely not taken. That doesn't sound good, right? I don't want it to check for updates. Okay, cancel. Okay. So basically, in this case, the programmer provides a statically predicted direction. So as a programmer, you can do it actually. There are some languages that allow you to do it. Basically, you use those, what's called pragmas in the programming language that qualify a branch as likely taken or likely not taken. So I'm going to give you an example in the next slide. Basically, you say if likely X. Likely is a pragma in C language, for example, that enables the programmer to tell the compiler, I think this branch is going to be likely taken. And that gets communicated to the compiler, and the compiler sets the hint bit based on this information saying, oh, the programmer thinks this branch is likely taken, so I'm going to set the hint bit as 1, and the hardware can use that information. So this doesn't require profiling or program analysis. The compiler doesn't need to do much. And the programmer may know some branches and their program better than many other analysis techniques, because there may be some semantic information that the programmer has that is not accessible to the compiler, right? Because the compiler may not know the intent of the programmer when the programmer programs, but now the programmer may communicate the intent in a very crude way, of course. Of course, now the downside is you actually have support across the entire stack almost. It requires support from the programming language. The language needs to enable you to do this. It requires support from transferring that information to the compiler, and then the compiler transferring that information to the instruction set architecture. So you still need the hint bits in the branch instruction format to be able to do this. And it may burden the programmer also. But you can say that this is a hint bit, the programmer doesn't need to do it. But if the programmer knows their code, maybe they can do it and they can get better performance. So let me talk about pragmas. Pragmas are essentially keywords that enable a programmer to convey such sort of hints to lower levels of the transformation hierarchy, to the compiler, to the hardware. So this is the example. If I know that this branch is likely taken, maybe I should use this pragma likely in the C language and indicate to the compiler that this is going to be likely taken based on the programmer's opinion. If this is checking for an error, you can use unlikely. This branch is unlikely to execute the taken code because most of the time you don't expect an error in a program, right? So it can communicate this information. And there may be many other hints and optimizations that are enabled by pragmas. I'll give you one other example, not related to branch prediction, but whether a loop can be parallelized, for example. In the OpenMB parallel programming model, you can have a pragma. Before a loop, you can say, I think this loop can be parallelized. So this is a description directly from the OpenMP documentation. Basically, this directive explicitly instructs the compiler to parallelize a chosen segment of code. This is another example of a pragma. The programmer thinks that this can be parallelized. Now, of course, the compiler can later check and make a decision differently from the programmer. So you communicate the hint, but you have no control after that. If somebody wrote a compiler that thinks they know better than the programmer, your hint might be useless. Right? So you may not have guarantees that this is going to be passed all the way down to the stack. Similarly, for the hint bit set by the compiler. The compiler may set the hint bit, but hardware may ignore that information, right? Why? Because the hardware designer may think, okay, I can predict this branch much better. That's possible. And that may be true, as we will see. So basically, all of these previous techniques can be combined. I'm not going to go through how would you do that. You can think about that. But there's a common disadvantage to all of these techniques. And it's in this word over here. They're basically static. They make use of no information that's happening while the program is running. Basically, you may have branches. A branch may change behavior dynamically. It's not always taken. It's not always not taken. But there's no way to encode this with the techniques that we've discussed. For example, the branch that you saw, taken, not taken, taken, not taken, taken, not taken, taken, not taken. It's very, very predictable. You just recognize that pattern and predict the branch correctly. But these techniques, static techniques, cannot do that. So you can potentially have a dynamic compiler, like a compiler that generates code at runtime while the program is executing, like the Java just-in-time compiler, common language runtime, a lot of the managed languages where you compile code while the code is executing. You can figure this out potentially and change it, but it has overheads also that we're not going to discuss. So a more sophisticated direction prediction is actually dynamic. So we'll cover the first one, and then we'll stop. So basically, you make use of runtime information that was not available clearly to the programmer or the compiler. So basically, the idea is very simple. Predict branches based on dynamic information collected at runtime. And the advantage now is you know the history of the branch. You can guess better. And we will see how to guess better progressively. You can adapt to the dynamic changes in the branch behavior. You can recognize pattern, taken, taken, not taken also. Taken, taken, not taken, 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 not taken. And you can increase that. There are many, many patterns, right? It's essentially a pattern recognition in some way. Or people actually right now use learning, machine learning techniques, like very simple perceptron-based predictors are there in some processors. So there's no need for static profiling. So input set representative problems goes away. But of course, there's a disadvantage. It's more complex. It requires additional hardware, and we'll keep adding more hardware again to get higher performance. So let's talk about the simplest possible predictor that you can build, last time predictor. So it does what it says, basically. You basically have a single bit per branch stored in BTB. You dynamically change that bit. This indicates the direction this branch at program counter X went last time it was executed. So the first time it's executed, assuming the branch is taken, you set that bit to 1. The next time you fetch that branch, you predict it as taken. In this case, it's correct. You execute it, you figure out you were correct, you set the bit to 1 again. Well, you don't change the bit, basically. The next time you fetch the branch, you predict it as taken again. And then it's again correct. So it's correct until here. Here, you fetch the branch, you predict as taken. Last time it was executed, it was taken. That's why you predict as taken. But it turns out it's not taken. So you mispredict whenever the branch switches direction between consecutive executions, right? So if you have this pattern repeating in a loop, you get 90% accuracy because you mispredict in this switch, taken to not taken switch, and you mispredict from this not taken to taken switch, right? Assuming that this pattern repeats in a loop. So 90% accuracy, even in this pattern, you get 90% accuracy, which is great. So, but the downside is always mispredicts the last iteration and the first iteration of a loop branch. Basically, you can think of this, you mispredict here and you mispredict here. So accuracy for a loop with n iterations is n minus 2 over n. So actually, if you want to think about the loop, it'll be like this. You execute the loop 10 times, and the last time, the 11th iteration, you fall out of the loop. Later, you come to the loop, execute it 10 times, you fall out of the loop again. So basically, with n iterations, you get n minus 2 over n accuracy. So if your n is large, this is great. Number of iterations is large. This works very well. The problem is, if you have a small loop like this pattern that we've seen, taken, not taken, you get 0% accuracy, right? Because last time prediction is always exactly opposite of what this time is going to be. So we're going to fix this problem next time after we implement the last time predictor. Have a good break. I'll see you next time.